So let's get the pronunciation right. Okay. This is a Greek letter. It's the Greek letter chi. Chi. Okay. These are the things that you need to know before you go off to college, or Greek letters, right? It's pronounced chi, or maybe chi, chi squared. And if you're in biology or have taken biology, you may have done these before. So the idea of a chi-squared test for goodness of fit is this. We compare the observed counts from our sample with the counts that would be expected if H naught is true. The more the observed counts differ from the expected counts, the more evidence we have against the null hypothesis. In general, the expected counts can be obtained by multiplying the sample size by the proportion. And that is within each of the categories, in each category. Right? So here's how you find the chi-squared test statistic. You're going to take the observed minus the expected. Then we square that. And then we divide that by the expected. Okay, so what we're looking at basically, what is it supposed to be? And then what is it actually? Okay, and so you're looking at the difference between what it should be and what it actually is. And the greater that difference is, the more evidence we have against the null hypothesis. That makes sense? Okay, and so we square them to get rid of negatives. All right, and then we get the test statistic for each category. And then this sigma right here, we're going to sum all of those up. And from that, we will get a p-value. All right, and then conduct our inference test. All right, so I think what I want to do is I want to skip example number 1 and come back to it and do example number 2, because it works out some things for us. So let's go ahead. Let's go ahead and go to this one right here. And we'll work through this and then do a chi-squared goodness of fit test. Okay, so it says, does the color of a car influence the chance that it will be stolen? The Associated Press reported the following information for a sample of 830 stolen vehicles. 140 were white, 100 were blue, 270 were red, 230 were black, and 90 were other colors. Use the goodness of fit test and the significance of 0.01 to test the hypothesis that proportions stolen are identical to population color proportions. Suppose it is known that 15% of all cars are white, 15% are blue, 35% are red, 30% are black, and 5% are other colors. Okay, so we need to make 2 columns, the observed counts and then the expected counts. And so they give us the observed counts. There's 830 total. And then 140 were white, 100 were blue, 270 red, 230 were black, and then 90 were other colors. And so now we need to calculate the expected counts. And we do that by taking the sample size, which in this case is 830, and then multiplying it by the percentages that they give us for each category. Okay, so we've got, and you need to show the expected counts, okay, because that's part of the conditions for a chi-square test. So we've got 830 times 0.15, and then 830 times 0.15. Oh, stop. 30.5, and then we've got 830. It's 0.35. And 830 times 0.3. Okay, I think I'm back. Sorry about that. Then we have 90, and that percentage was, sorry, it's not 90, it's 830. Times a percentage that was black, which was 0.05 for the others. Okay. And so you need to go ahead and write the expected counts down. I rounded to 1 decimal place, all right, which doesn't make a whole lot of sense in terms of the context of the problem, but go ahead and leave it with 1 decimal. So this is, I got 124.5. And then 290.5, and then 249, and then 41.5. Okay. And so when we're working these problems, you need to show the expected counts. You do not really need to do the next step, working it out, but I wanted to show you the math behind the problem, but we're going to use our calculator to calculate this. And so here's what I want you to do. Okay. For each category, take the observed count, subtract the expected count, square that gets rid of the negatives, and then divide it by the expected count. So for the first one, I got 140 minus 124.5, and then we square that, and then we're going to divide that by 124.5. So do that on your calculator real quick. And somebody help me out. What'd you get on that? Okay. I got like 1.9297, something like that. And then we're going to do the same thing for the next category. So we've got 100 minus 124.5, and then we square, and then we divide by 124.5. And I got 4.8213. And then 1.4466, 1.4498. This one is 56.681. Okay, and so if you notice, these are the values for each category. And to find the overall test statistic, we're going to add all of those together to get the sum. Okay. And like I said, your calculator will do this for you. So if I add all of these together, I'm going to get 66.3284, which is the sum. Yes.
Does it matter how many decimals you round it to?
No. Like I said, you probably won't even do this when you're actually doing a chi-square GOF test, because your calculator will give you this value. Okay, but this is what the calculator is doing. It's doing that for each of the categories and then adding all of those up. But let me ask you this. Just postulate an answer. Based on this, do you think that we will reject H naught or fail to reject H naught? How about you do this? Turn to your stats neighbor real quick, and I want you to say 3 things. One of 3 things. Reject H naught, and then why? Fail to reject H naught, and why? Or I'm not really sure. Can you help me out? I'll do that real quickly. Okay. Come back to me, please. And we're gonna work through the problem real quick, and then we'll see if you were right or not. So the hypothesis and hypotheses for chi-square test is a little bit different. Whereas we used some symbols previously, whether it's mu or p. Here I'm going to write these out. And so the hypothesis, the null hypothesis, is the true proportion of cars stolen equals the population color proportion. So that's my null hypothesis. So what's my alternative?
First one is not equal.
Does not equal. Okay, so I'm gonna say the true proportion of cars stolen does not equal the population color proportion. And let me add one other thing to that. I'm gonna say for at least one category. So in other words, if one category is significantly different from what it is expected to be, that would cause the chi-squared test to have strong evidence against the null hypothesis. Okay, so here we go. Conditions for a chi-squared test. Number one, it's got to be a random sample. And I don't think that it mentioned that. It should be. Hold on, it says that they were, what does it say? Right here, it says random sample, right? Right there. That's what it says. Therefore, that condition is given. Okay, it's an SRS. The population of stolen vehicles greater than 10 times 830. Well, unfortunately, right, that's probably true as well. But the next condition is important. It is a condition specific to a chi-squared test. All expected counts must be greater than 5 to do a chi-squared test. Okay, so you've got to show that and check that. So that's why we did the expected counts column there. Okay, so all of our expected counts here, smallest one was 41.5. So they are all greater than that, which is all greater than 5. And so my conditions are met. When you're doing a chi-square test, you also have a degrees of freedom. And so the degrees of freedom is going to be k minus 1, where k represents the number of categories. Okay, and so there were 5 categories in this case, 5 different colors. So my degrees of freedom will be 4. Significance level of 0.01, and we're going to reject H naught if the p-value is less than 1%. Okay. So now we're going to take our little calculators. And second. Okay, so I need you to go to the spreadsheet here. And then I need you to make two columns, one with the observed counts and one with the expected counts. And also you need to label them. Right? And so once you get the observe and the expected counts in the spreadsheet, we're gonna run a chi-squared GOF inference test. Okay, so I'm going to go to menu, statistics, stat test. All right, and this is a chi-squared goodness of fit test, which is option 7 here. And then I'm gonna put in the observed variable and the expected variable. And I also need to put in the degrees of freedom, which in this case is 4. And I'm going to hit OK. All right, so look, a couple of things. Right here, I got my chi-squared test statistic, which is 66.3282, right? Which is what we calculated there when we added all of those up. But careful right here, because look at my p-value. What is my p-value? It can be 1.35, right? Because that's not a probability. It is 1.35 times 10 to the negative 13. Okay, which is essentially 0. So let me go back to the notes here and write in some things. So we've got my test statistic was 66.3282. I need to say the name here. This is a chi-squared goodness of fit test. And what the calculator is doing to get the p-value, it's going to do chi-squared CDF from 66.3282 to positive infinity with the degrees of freedom of 4. And so if you were to put that into your calculator, you're going to get the p-value of 1.35 times 10 to the negative 13. Or that is approximately 0. Okay, so 1.35 times 10 to the negative 13 and DF of 4. Yes.
Does that work, or do we need to like plug it into that formula? Like, we're doing a problem?
What are you talking about?
Test it. Expert, we need to plug in that work.
I think this is enough. Okay. I would kind of like you to show the chi-squared CDF there, but I think if you have that and that, I think that's probably sufficient. Okay. But I will double check that against a rubric off an FRQ, and if something's different, I will let you know. Okay. And so since my p-value is less than alpha, we are going to reject H0. Okay. Did you say reject at the beginning? I think if you look at this category right here, I got 56.681 for the observed minus expected squared divided by the expected for this category. Okay, and so that is significantly off from what it was expected to be. Therefore, that is evidence against the null hypothesis. Okay, so my conclusion, we are going to reject H naught. Since p-value is less than alpha. Alpha was 0.01. So there is sufficient statistical evidence to conclude the true proportion of cars stolen does not equal. Okay, you got to put it in context and you got to give the correct conclusion there. So does not equal the population color proportion for at least one car color. All right, here we go. It says, according to the 2000 census of all US residents aged 20 and older, 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, 15.5% are in their 50s, and 22.8% are 60 and older. The following table gives the age distribution for a random sample of US residents aged 20 and older. Members of the sample were chosen by randomly dialing landline telephone numbers. Y'all know what that is? It's a telephone with a cord that plugs into the wall. Didn't want to lose anybody there. Okay, just so you know. Okay, so we have the different categories. We have the counts. Okay, so those are the observed counts. We need to get the expected counts. So take your calculator and multiply the total by the respective percentages. Okay, so 19.1% in their 20s multiplied times 1048. And I'm gonna round to one decimal again. And I got these numbers for my expected counts. All right. Do these data provide convincing evidence that the age distribution of people who answer landline telephone surveys is not the same as the age distribution of all US residents? All right, so my null hypothesis is the age distribution of people who answer landline telephones surveys. And I'm just gonna say, the age distribution is not the same. Or excuse me, for the null hypothesis is the same as the age distribution of all US residents. So the null hypothesis is that the age distribution of those who answer the survey is the same as the age distribution of all US residents. the alternative hypothesis, the age distribution. People who answer landline surveys is not the same. It is not the same. All US residents. All right, so my conditions. We've got SRS. People. That is given. We've got the 10% rule. So the population of US adults must be greater than 10 times 1048. And that is true. And then we've got to have all expected counts must be greater than 5. And that is also true in this case. Okay, so make sure you do your decision rule. We're gonna let alpha equal 0.05 and reject H naught. Yeah, my p-value is less than alpha. And my degrees of freedom in this case is going to be 4 because there's 5 different categories. Chi-squared GOF test. Okay, so I'm gonna set it up and then you can use your calculator. So my test statistic is going to be chi-squared equals the sum of the observed minus expected squared divided by the expected. So go ahead and take your calculator and go to the spreadsheet and create 2 columns with the observed and the expected. And then run the chi-squared test, chi-squared goodness of fit test. So I'm gonna go to menu and statistics and stat test and chi-squared GOF. And it's gonna be observed. This is expected. And degrees of freedom of 4. And I got 48.229 for my test statistic. And again, I got 8.455 times 10 to the negative 10 for my p-value there. Okay, it can't be 8.455 because that's not a probability, a valid probability. All right, so let me go back and fill those numbers in. So this is 48.229. So we got chi-squared CDF from 48.229 to infinity to the DF of 4. And that's gonna give me 8.455 times 10 to the negative 10. So since my p-value is less than 0.05, we reject hypothesis. So there is sufficient physical evidence to conclude that the age distribution sure. The online surveys is not the same as the US population. I want to say as the distribution for the US population.